Welcome everybody. Thanks so much for attending LISA 14, and thank you for attending this track today. We're very happy to have Dustin Kirkland, Canonical's product manager here with us today. Over the next 90 minutes, he'll be showing the best methods and practices to deploy and scale OpenStack. Please help me welcome Dustin.
Thanks. Suppose you want to see the screen, right? All right, so in the introduction it says we're deploying and scaling OpenStack. That's too bad because I was all ready to deploy and scale Hadoop. But I guess you don't want to see Hadoop. You're here to see OpenStack, right? In that case, let me go ahead and destroy this environment so we can start all over and deploy OpenStack. So I'm going to run 98 reset and get our environment reset. Deploy and scale OpenStack then. That's what we're going to do. We're going to do it right here on real hardware with lights that blink. You can't fake that, I'm telling you. You just can't fake that. If you're here, you've probably seen the abstract, but basically we will start by deploying OpenStack to these machines right here. We'll go over each of the OpenStack components just to make sure we have the appropriate vocabulary to talk about the various pieces of OpenStack. Once we have an OpenStack up and running, we'll see what a brand new, never been used OpenStack looks like. And as you may or may not know, when you first start with OpenStack, it's not quite ready to be used out of the box. There's a bunch of things we're going to have to do. We're going to have to create users and upload keys and upload images and configure networks. There's a bunch of things that we'll have to do to get that OpenStack up and running. But we'll go through each of those. And then we'll finally launch instances. And we'll launch a couple of instances by themselves. But ultimately, if you're setting up an OpenStack, maybe you have some users who just need an SSH shell into a running instance. But you might also be interested in running workloads, real workloads. Maybe we can get back to that Hadoop workload we were going to look at here until you guys shot that down and said you wanted to see OpenStack deployed. And then if we've got time, we'll blow it away and we'll start all over again. And we'll do that one without the sort of instructional pauses in between, and we can see how fast we can make it go. Let's see if our reset is done, and it is. So first of all, if you want to see what, actually let's kick off the deploy, and then we'll take a look at what reset did. Okay, OpenStack releases. Icehouse or Juno? What do you guys want? Now Juno was only released like 2 weeks ago, so there might be big problems with Juno, and then we're going to have to debug them if we go that route. Or we can go Icehouse, and it's perfectly safe, and everything will just work. What do you want? Juno? Juno. All right, let's do this. Juno on Ubuntu Trusty. We're going to run 0.1 deploy. First of all of our lights off except one? Yes. Okay. All right, so we have reset the environment, and we are going to deploy OpenStack Juno. Do we have lights coming on yet? Does anyone see any lights coming on? Someone raise their hand when they see lights coming on, just so that I'll know that. Oh, okay. You got a blink? All right. This might work then. So this will take about 10 minutes, 12 minutes maybe, for this step of the process. During which time we're going to talk about the components of OpenStack and introduce you to our little piece of hardware here that we call the orange box. Is anyone familiar with the orange box? Have you seen it before? Got one? Okay. It's a curious little kit here. I'll show you the back since you can see the front of it, right? There are 10 physical servers inside of this machine. It's 10 Intel NUCs. Anyone know what a NUC is? Anyone have a NUC? They're the coolest little machines. It's a 4-inch by 4-inch motherboard with everything you'd need out of a computer, and it's literally like that big. And so we took 10 of those, we took them out of their nice little plastic case, and we put them inside of a custom designed chassis right here. There's 5 nodes, 5 nooks across this heatsink and 5 across this heatsink. So these are aluminum heatsinks on either side. The way the board nests up against the heatsink, the CPU and the video processor are touching the aluminum, and so there's no fans on any of these boards. They're all completely fanless. They're all SSDs, so there's no moving parts on any of our 10 servers. Each server is basically a quad-core i5 with 16 gigs of RAM and 120 gigs of SSD storage, and they're all identical, except for node 0, and that was the light on, I guess, your far left that was on. It kind of stays on all the time. That's going to be our management node. That's the node that controls the other 9 while it's doing its thing. The only difference about node 0, other than it doesn't get reinstalled constantly, it has a Wi-Fi adapter, which is our internet uplink when you need that sort of thing. And it has a 2 terabyte spinning disk also associated with it, and that allows it to, we can cache a whole bunch of stuff. I primed a cache here before we got started, which can help speed things along a little bit. So yeah, that's the orange box. I guess if you're looking at the rear, oh, there's also a gigabit switch on the inside. So everything is connected internally on a gigabit switch. There was a 16-port switch. We had 16 extra ports, so we exposed a few here and put them on separate VLANs so that we could have a management network and other stuff. It plugs into 100 to 220 volt anywhere. The power supply is rated for 300 watts. The most I've ever managed to pull out of it's about 210 watts. And I was running a transcoding job that basically pegged every disk and every CPU and the RAM on every system. And then when you're running normally, it's 20 or 30 or 40 watts. It's really an efficient little box. Fits in a flight case that I'd lug around the world to do demos and instructional conferences such as this. Let's take a quick look at where we're at. Okay, still moving along here. I'll put this in a watch, Juju pprint, and let that go. Oh yeah, and if we cracked it open, it would look something like this. I guess I should have said that when we were talking about how the boards are associated. Okay, so that's the hardware. Any questions about the hardware before we talk about OpenStack? Come talk to me after it. I love geeking out about this box. It's so much fun. So the OpenStack components. This may be reviewed for some people, but I know some people I was speaking to before the session, this is really their first introduction to OpenStack. So bear with me for a couple of minutes while we finish deploying here. Nova. Nova is, I guess you'd call it the heart or the beginning of an OpenStack. Nova is the compute portion of OpenStack. It's what hosts and provisions virtual machines. And those virtual machines today can be on any one of a number of different hypervisors. Of course, there's the KVM hypervisor, but also there's Xen and VMware ESX, even Windows Hyper-V. A number of us are working on supporting Linux containers as another option for guest instances to run inside of a Nova. It was one of the first 2 components that formed the very first OpenStack, the OpenStack Austin release back in 2010. It was Nova and Swift originally. To a large extent, Nova was contributed by some work NASA had done around building an open source infrastructure as a service cloud, and that coupled with the Swift object storage bits from Rackspace is really the genesis and the earliest 2 components of OpenStack. Neutron is the networking piece of OpenStack. I probably should also map some of this to Amazon. I assume people are familiar with AWS or Amazon. Nova is equivalent to the EC2 part of Amazon Web Services, AWS. So it's the virtual machines aspect of the OpenStack cloud. Neutron is the networking piece, network as a service, you might call it, or network connectivity as a service. It's programmable to a large extent. This is this kind of combination of SDN, software-defined networks, and network functions virtualization, NFV. Those two pieces, where that fits into the OpenStack arena, is really inside of Neutron. It's got an API for provisioning networks, creating networks, deleting networks, attaching machines to networks, allocating IP addresses. It's also probably the most pluggable aspect of OpenStack. And what I mean by pluggable, I mean it's the place that many of the vendors that come together and work on OpenStack, this is where many of those vendors have value-add commercial services that plug in or fit on top of a standard OpenStack. So you'll have Cisco and you'll have Juniper and Cumulus and other network vendors will provide plugins to Neutron that will allow you to drive Neutron like their traditional network hardware. Okay, so this is really network as a service portion of OpenStack. Swift, I mentioned before, was really with Nova, one of the first projects in OpenStack. Swift is object storage. So again, back to Amazon land, Swift is like S3. It's your blob storage, your object storage. You'll see a theme here. It's really about, OpenStack is really about APIs. So going back to Nova, it provides an API for creating virtual machines. Neutron provides an API for creating networks. Swift is really all about that API for object storage. It's what you get when you get S3. It's an HTTP-based RESTful API for allocating and actually managing those objects. They're distributed. They're distributed across the Swift cluster, replicated. It scales out to extremely large clusters. There was a fantastic talk earlier this morning. Learned a bit about SwiftStack. SwiftStack being a solution built on top of Swift. Cinder is the block portion, the block storage portion of OpenStack. So again, mapping to AWS, this is EBS. This is sort of like elastic block storage. It's what gives you the persistent storage feeling, or the persistent storage feature that you attach to instances in an OpenStack. So OpenStack boots like an AWS, typically with ephemeral storage that's local. If you want persistent storage, you need Cinder. You need that EBS experience. And you understand the difference between block storage and object storage? Mostly heads nodding. Okay, good. Horizon is the graphical interface. It's the web interface for talking to your OpenStack. It's how you as an administrator can configure many of the complex configuration options. Of course, you can do those from a command line. We'll do a bit of both in our demos today. But it's also got a web UI, a skinnable web UI. What you'll see today is the Ubuntu Horizon interface, but it's literally a CSS file you can drop in and replace that interface with your own customized Horizon web interface. It's not just for administrators, though. It's also for the users of OpenStack. So the users can log into Horizon and list their instances, create instances, destroy instances, do all sorts of things with their instances. I said log in just a second ago, and you log in requires the Keystone service. Keystone is all things identity and authentication in an OpenStack. Like Neutron, Keystone is very pluggable as well. There are plugins that you can use to attach your Keystone to your Active Directory or your old app, your existing user base, so that when you install an OpenStack, you're not just creating a whole nother set of users that have to manage. You can actually leverage existing user databases through plugins to Keystone. It's also used more than just for the authentication of individual users, but also for services itself. Services authenticate to other services using credentials that are managed by Keystone. Glance is the image repository. Images, when I say images, I mean something like an AMI, an Amazon Machine image here. It's OpenStack images. Glance is the repository of all of those images including the metadata about those images. So, you know, the who, the what, the when, the where, the why, everything about that image and the image itself is stored in Glance. Glance, the back-end storage for Glance is typically provided by your block storage mechanism, so Swift or whatever the block storage mechanism might be. And every time you launch an instance in Nova, in OpenStack Nova, the compute portion, you specify what image you want to boot in Nova, and Nova retrieves that image from Glance and then basically clones a machine and launches a virtual machine there. Scalability is basically metering for all the components of OpenStack. So, you know, there's a lot of different users driving the development of OpenStack. Some are individuals or companies that want that AWS experience but need to do it in-house, need to do it behind their own firewall for various reasons, perhaps compliance, security, cost. In some cases, it's just because they've got a whole bunch of hardware and need to do something with it. And an easier way of managing that hardware is taking advantage of cloud-like functionality to virtualize instances on that hardware. Another class of users, though, are service providers. It's smaller clouds. It's the evolution of ISPs or hosting providers that are looking to modernize their infrastructure and use something like OpenStack. And for that, Scalability collects the usage statistics for all the components of OpenStack, and then rules can be applied to those usage statistics for billback. And it might be internal billback, you know, what part of the company is responsible for OpenStack. It might be for consumption of resources by public users of that OpenStack. Heat is a templating engine that's part of OpenStack. It's one of a number of different ways to orchestrate workloads and applications into an OpenStack. It's worth mentioning. It's one of the OpenStack projects. We're not going to do much with Heat here today, but it's definitely something that you may want to look into if you were familiar with like a CloudFormations project in Amazon. Trove is another very recent addition to OpenStack. Trove is a database as a service, a cloud database as a service. It would be similar to an RDS, I think is what Amazon calls it. It's what allows end users of your cloud who simply need a new table in a database, and they just want that database centrally managed and highly available and replicated and always up and running. You know, I just want the database as a service. Trove is that project within the OpenStack ecosystem. And the newest component, which we don't even have a fancy logo for yet, is the Sahara project. And Sahara is very similar to Hadoop. To database as a service. It's more like Hadoop as a service, or it is Hadoop as a service. Again, that maps again to similar offerings from I think it's MapReduce as a service, Elastic MapReduce EMR from Amazon. So we are nearly done. That might be a little bit too small, huh? Let's get a little bigger. One more, or is that okay? One more? Okay. So let's take a look at what's going on. We're almost done with our deployment. We'll let this finish while we take a look at what's happening. I've split my screen into a couple of different windows. These are all shells on the master node. So on node 0 here, on that master node, we've got a shell where we're running, this is Ubuntu 14.04. At the very bottom is a running log that we're tailing of what our installation itself. And it's currently establishing hundreds of connections between all the different services that are running on all of these different nodes It's establishing those connections and ensuring that everyone is talking to everyone and that everything is authenticated and those connections are in place. This section, anyone recognize that log? It's a squid log. This is what I'm using to accelerate the process of deploying this. We're on shared conference Wi-Fi. By the way, I noticed the bandwidth in here went all the way through the floor as soon as people started filtering into the room, and it's really, really good that we've got almost everything that we're installing here located in the squid cache, so we can survive the slow throughput right now. But yeah, so that's the squid cache. It's running also on node 0 here. This is the shell where I launched the deployment, and there we go. It finished in 1,000 seconds, so a little over 10 minutes. About what's that? About 15 minutes or so. I know I tested the deploy earlier this morning from my hotel room, and it actually took me longer to iron my shirt than it did to deploy all of OpenStack here. And then here we have just kind of a text view of the various services that are running as part of our OpenStack. So here we can see, I may have to scroll a little bit. Let's do a QG print class. Okay, so we went over a bunch of services. One that I didn't have a slide for is Ceph. We're actually using Ceph behind our Swift and our Glance and our Cinder. Ceph is a distributed file system that is providing a clustered storage solution for us. So these are all the services that are part of our OpenStack here. We've got a Ceph gateway, which is the gateway is the piece that ties all the different Ceph storage nodes together. We have a Mongo database. Mongo is actually the NoSQL database where Ceilometer is streaming all of its statistical information. We have the Nova Cloud Controller. That's the piece that decides on what Nova compute node will this machine be scheduled onto. We've got our multiple Ceph workers, one here, one here, one here. We have our Heat server. We have a MySQL server. We have our Glance server. We have Ceilometer. We have a Nova Compute, 1, 2, and 3 Nova Computes. We have a Rabbit MQ, a message queue. This is how all the messages are prioritized and delivered throughout the entire OpenStack system. We have our Keystone. We have our dashboard, which is Horizon. We have Cinder, the block storage. And we have our Neutron gateway, our networking gateway. And then underneath each of these, you can actually see on what physical system this is running on. It's more for debugging purposes, but sometimes it's useful when you've got a service that's misbehaving and that you don't have a light on, and that you need to go to the lab and see what's wrong with that server. But here it looks like everything is started and up and running. So we will close out a couple of those. We will log in here and find out where our Horizon gateway is running and log into Horizon. Is anyone familiar with Horizon? Seen it before? Used it a little bit? Some? Okay, good. So this is a Horizon and the dashboard for all of OpenStack itself. Is that font okay, or do I need to increase it a little bit? Is it okay? Okay. Just say something if it's too small. So here we can get an overview of our brand new OpenStack, and there's really not much running in it right now. There's no stats or reports that we can run just yet. We can see our hypervisors, though, and we have 3 hypervisors, which happen to be running on nodes 1, 2, and 3 here. We have a total of 12 virtual CPUs. I said there were about 4 per physical node here, so we have 4 virtual CPUs that we can allocate without over-allocating or overtaxing our cluster. We have 46 and change gigs of memory that we can use. Sometimes your workloads are memory constrained, other times CPU constrained. And 335 gigs of disk available to us. And there's currently nothing running here. In fact, we can't run anything just yet because we don't have any images in our OpenStack. So we'll need to load some images in OpenStack. Moreover, even if we did have images and managed to launch an instance, we haven't defined any networks, which means that even if we started the instance, it wouldn't be able to draw an IP address, and even if it drew an IP address, we couldn't route our traffic to it to SSH into it or load a web server running on that. Networks also require routers, and if you've dealt with Neutron, I imagine if you've had this similar experience to me, it's very complicated. It's an extremely complicated system to wrap your head around. There's also a number of quotas that ship out of the box with OpenStack. Some of these will hit very, very quickly. The 10 instances, for instance, if we wanted to run some real workloads here, more than 10 instances, we'd hit that limit, and then we couldn't schedule any more instances. So in the system info, we can see all the different services from OpenStack and where they're running, on which physical machines, and so forth. Okay, so now, sorry, that's all under the administrative tab. I should probably also mention that to a normal user, a non-administrative user, they would only see the project section, where there they can see a bit about the resources that they've consumed or that they have access to, the instances that they're running, the volumes that they've created, any images they might have uploaded, and then their own credentials that they've provided to the system. So there is pretty decent role-based access control type functionality available in OpenStack. So now, before we can actually use this OpenStack, what we'll need to do is set a bunch of things up. Oh, I promised you we would look at those scripts as far as what they would do, right? So our reset script simply terminated all instances, and then I flushed a bunch of network connections to each of the physical nodes. Kind of a nasty little hack, but the out-of-band power management system on these NUCs is kind of wonky, and it leaves open connections a lot longer than it should, and then bad things happen. So that's a forceful way of flushing all of those out. And then our OpenStack, we did Juno, right? Yeah. Our deploy script very simply ran this command, juju deployer, on a Juno YAML file right here. And if we look at that Juno YAML file, you'll see all of those services. It's really hard to read, isn't it? It's a little better, right? This YAML file describes the OpenStack cloud that we just deployed, including all of the services that we just walked across, Ceph and Keystone and Nova Compute, Neutron Gateway, and so forth. It also has a little bit more information there as well. It says where to get the service code from, where to get we call it a charm, but where do you get the instructions on how to install this from, the number of units, and any constraints. So for instance, I want Ceph on physical nodes, physical machines. You can also set some configuration information, such as this is a randomly generated secret for managing Ceph, and you'll see that for a number of the services. So Keystone, for instance, default username or default password and token, admin, and so forth. This is 240 lines or so of YAML code, the majority of which is down here. And this is where the really interesting stuff happens. All the different relations, how these services have to relate to one another to be useful. This is the YAML description view of it. There's actually a graphical view we can look at as well. It looks something like this. Let's see if I can zoom in a bit. Each of these icons is a single project or a portion of OpenStack. This is Horizon, this is Keystone, Nova Cloud Controller, our Nova Compute, Neutron Gateway. This is the GUI itself. Oops. NTP, we're running an NTP service. Scalability here. RabbitMQ, MySQL, Mongo, Heat. Every one of those lines here relates or describes a relationship between one of these services and other services that it either depends on or provides. So you'll see everything is related to the NTP server. That's how we keep time in sync across all of the machines. But you can also see that Scalability here requires a MongoDB. And this relationship is what explains how the MongoDB service has to be in place and has to be associated. Scalability has to have a connection to that MongoDB service to be functional. You can see that for every one of these things. Glance, for instance, provides images for the system, and Glance needs to store metadata in MySQL. It needs to provide those images to Nova Compute here. This is the Nova Cloud Controller. The Cloud Controller has to retrieve those images from Glance. Keystone is associated with Glance for identity and authentication. Glance stores information in Ceph here as our block storage, and of course it relates to NTP as well. So that's the sort of the description of how things gets installed. Now we wanted to configure OpenStack itself. So I've got this script, orangebox configure OpenStack, that under normal circumstances I would just run. But what we'll do here is we'll look at each command and make sure that we understand what's going on. So we'll copy and paste them from the top window to the bottom window. So first of all, we may need a bunch of packages that would allow us to issue commands directly to OpenStack using their APIs. And as it happens, I've already installed Python Keystone, Python Neutron client, Python Nova client, Python Glance client. These are the different client commands that we'll need to run to configure our OpenStack. And I'll set a bunch of variables here, and we'll talk about what those do right here. So I guess I should probably mention a little bit about the network, and it's hard to explain the network without explaining how the box is wired up. We tried to model this network after how you might set your network up in a data center. And what we did was essentially model a rack of machines. There's 10 nodes in here, but just add zeros to that. You might have 100 nodes or 1,000 nodes that might fit inside of here. Every one of these nodes has a network connection to a switch inside of this box. And the master node is actually providing DHCP and DNS, and I showed you the squid proxy. It's acting as a gateway, so all of the machines are behind that master node, that node that's orchestrating everything. It's on a 10.14 network. It's a /16 network. It gives us hundreds of thousands of IP addresses, which we don't use hundreds of thousands of IP addresses, but we have used thousands of IP addresses on hundreds of virtual or thousands of virtual machines on these systems and containers especially. So the external gateway is 10.14.4.1, and that's actually the address, the internal address of the master node here. It also has an external address. It's acting as a gateway to go out. But the internal address is 10.14.4, and that's going to act as the gateway for every one of the instances inside of the OpenStack that needs to route its traffic out. I said it's a /16 network that gives us 255 times 255 addresses. We need to give that network a name, and this is the external network. That machine is also running DNS. So we're performing DNS resolution for the physical nodes inside of this box, and it's forwarding those requests on. It's just a bind 9 server. It's set up in forwarding, so it'll go out and ask the internet, any addresses it doesn't know about. And then we need to create a floating address range. This is the range of IP addresses that Neutron will assign and attach to instances that you require external IP addresses for. So in like an Amazon world, right, you've got an internal address and you've got an external address. The internal address is nice because you can stay inside of that cloud, inside of that network. You're not going out past the firewall. You've got 10 gigabit a second connection. You also don't have to pay for that traffic, especially if you're moving terabytes of data around. But you also need that external endpoint if you want to be able to get into the system. So this is a range, a rather large range of addresses that when we do ask for a floating IP, is what it's called, associated with our instance, this is where it's going to, it'll come from this range. And then we've got this internal administrative network, or we're calling it admin network, but it could be external network and internal network. The internal network is the network that the instances will be able to communicate on inside of the machine. All of this is handled by Neutron. That's really the magic of Neutron, creating these networks and assigning those IP addresses and routing that traffic. You can imagine this gets very, very complicated. It also, will be inevitably different than this in your environment, but we found this works very well for this sort of constrained environment, and actually for environments somewhat larger than that as well. So we've set these variables here, which we'll use in a minute. We also will need we'll need to get our keystone server. So this command, go keystone. So our keystone server is running on node5.mas. I could have also gotten that IP address for node 5 as well, but since we're running a DNS server, let's use host names. That's nice, right? Because we're going to need to add some information to a Nova RC file. This is a bit of a convention, but most people who set up an OpenStack will create a Nova RC file that defines these variables. These are variables that the Nova command line, the OpenStack command line clients. Those OpenStack command line clients respect these variable names basically. So you have a service endpoint, you have a service token or password, you have an auth URL, username, password, etc. And these we'll set here, and then we will source that configuration file that we just wrote. We wrote it to a configuration file or an RC file because that's something we'll use over and over and over again in an OpenStack, as opposed to the rest of those shell variables, which we just need it to run this one script. We also need to get the tenant ID. The tenant ID is randomly assigned when installing OpenStack itself. So this is going to be a big MD5 sum or hash or whatever that is. We'll need that to run some commands across as well. So now we fetch our external network ID, and we do that by running this Neutron command. So this is where we start to run these command line interfaces to talk to Neutron. Neutron create, net create, external net, tenant, you give it a tenant ID. Looks like this projector's cutting off the right part of the screen. Or not. Okay. Something's eating my buffer, video buffer here. So that's our external network ID. I guess it's worth mentioning that this information is available in the GUI. We could click through the hundreds of screens it would take to create a network, select a project, name it, etc. What we find is it's a lot more repeatable to create a shell script or create some scripts that do this for us. Any way that you're going to install an OpenStack, there's a lot of different methods, Puppet methods, Ceph methods, etc. Almost all of them are going to use these command line tools to set it up. So we've got our external network ID, and now we run the Neutron command that's going to actually create our subnet. And this one's worth looking at because this is sort of the effect of what has to happen so that your instances can have IP addresses on an accessible network. So that Neutron command, that's where we feed it those variables we set above the network, the sitter, the allocation pool, the start, the stop address, and it's all reflected here. And the tool actually has a pretty output of what that taking effect. And now if we refresh here, you can see that we now have an external subnet associated with it. And it's the 10.14.00/16. So now we have our external network. We need to create our private network. So we'll run the Neutron create private network command. Now if we refresh here, we've got a private network. And we'll need to sorry, I lost track where I was. Here we go. Now we need to get the subnet ID, of course. So we'll run that, and we'll see that we now have a subnet ID. And again, that's right here. And now we need to create a router so that the traffic can move across the network. So if we look at our routers, we see those are currently empty. Did I misspell router? Okay. So we've got our router. And then we need to attach two interfaces to that router and set the gateway. And with that, we've got our external network. We have our gateway associated with it, internal gateway, external gateway, and the state is up. So that's all good. We now have Neutron configured. The next thing we'll do is modify our security groups. So this is, I can't tell you how many times this bit me before we finally scripted this out, and how many people I've also seen this bite. You get everything configured, you've gone through the whole Neutron setup, you launch your first instance, and you can't SSH to it. And you just beat your head against the wall. You got to open the firewall rules. So by default, let's see, where's the security? Under projects, access, and security. Yeah, so the rules in the security group, there are, it's closed off to the entire world. So the default is the most strict, and you have to open the various rules. So we're going to open ICMP so we can ping our instances. We're going to open 22 so we can SSH to our instances. And although we're not going to use that here today, we'll also open 3389 so that we can RDP into Windows instances if we were to start Windows instances on an OpenStack. So now we have security rules. We are allowing ingress of ICMP and TCP for our instances. So we can actually get to them now. Next, we need to upload a key pair or have one generated for us. As it happens, I've got a key pair in my SSH home directory, and so I just send it my pub key, and I think that's under the user. identity. Excuse me? Ah, you're right, you're right. Key pairs, thank you. So there we go. So that's our SSH key, which is now uploaded, which will be inserted into our instances when we run them. Now, one really cool thing about OpenStack is the ability to modify your instance flavors. So these are the instance flavors that are available out of the box. There's this tiny instance with one CPU with 512 megs of RAM, all the way up to extra large with 8 CPUs and 16 gigs of RAM. As it happens on our orange box, we don't have any systems that have 8 CPUs, so we'd like to delete that flavor. And as it happens, the M1 Tiny instance, for any of the workloads that we typically run and demo on the orange box, that's usually a little too small to do the useful things that we want to do with it. And so what we often do is run these two commands to delete those flavors. Now this one, again, all of this is very editable on the command line or in the GUI as well. I'll change. We can change this to. Let's modify one of these for fun. So if we edit this, we can change this to 4096, so 4 gigs, and 80 is way too big for these little machines, so we'll save that to 40. And now we'll make our M1 medium a little smaller as well. So we'll do 3072 here and 20 gigs. So you can really, and then you can create your own flavors. So you can create a F1.Red Bull if you want, and give it 3 CPUs and a gig of RAM and a 10 gig root disk. Field required ephemeral. So tell that 0 and 0 gigs of swap. Create a flavor. So now you can create completely arbitrary images, arbitrary names. And that's useful if you really want to tune your images to your workloads. There's also a handful of quotas that we often want to change and modify. The number of let's go back to quotas. Resource usage. Forgotten where the quotas are. Server identity, users. Resource usage. Nope. Hypervisors. Nope. What'd you say? It's under defaults.
Yeah,
under admin, system, defaults. Thank you very much. Haha, there you go. Well done. Bonus points. So there's a number of quotas that can be modified. The ones that we end up modifying typically are the number of instances allowed per user. So I set it to 100 here. The number of cores allowed that for a user, the amount of RAM that a user is allowed to use, and then this is the one. Oops, this is the one that bites me all the time. The number of security groups. So security groups are the rules associated with the network traffic, and we find that we'll blow through that 200 security groups in a complex cloud very quickly. So now if we refresh this here, I don't know if anyone saw the differences take place, but I can assure you they did. And then finally, we need to upload some images. So I'm going to upload Ubuntu Precise, which I happen to have local on the system. Normally you would go to cloudimages.ubuntu.com, and you could click through here and download the .img file. That's all that I've done here. This image right here is the image I've just uploaded, and I'll upload Trusty as well, which you could get from a similar place. Of course, you could upload images from a lot of different operating systems. Here's CentOS, here's Cirrus, even Windows as well. So now if we look at our images available to us, you'll see we have our Trusty image and our precise image. If we look at that, you can see a bit of metadata about this image. The size is 244 megs, it's a QCOW, and so forth. And now that we've done all of this, we can actually launch an instance. So we'll click the launch instance. We'll do something in the GUI here, I guess. This is our test 1, and we can choose our flavor type. We'll do an M1 small. We want one instance, although we could actually let's do 3 instances. We'll go bigger than that too. We'll go M1 medium. And we want to boot from an image. We also could boot from a snapshot or a volume if we had those, but we're going to boot from an image, and we're going to run Ubuntu Trusty. And you can see a bit about your limits. I think I'm going to click launch. It's going to say, no, you have to tell me what network you want. And I will give it the external network so that we can actually SSH into this network. And then access and security, my default key pair has been chosen. You could actually run some scripts on after your instance loads, and then you could modify the disk partitioning. But at this point, we are ready to go. So we'll launch these 3 instances, and we'll see that they are coming up and have gotten IP addresses associated, and process of spawning. Let's try pinging one and see if it's up yet. Not yet. We'll see this little Ajax GUI refresh, and wow, there it's running. And we should get a ping here in a second. Cue the music from Jeopardy. I put the wrong network there. Let's try this again. We'll launch one more instance. They're cheap, right? Test 2, M1 medium. Boot from image. Trusty. Actually, I think that is going to be what's wrong. And once that's started, then we need to associate. Yes, that's exactly what I did wrong. Okay. So now that that's running, we need to associate a floating IP. And we add one of those. Allocate an IP. It's going to be .5. Aha. Now you see the difference here. We have 2 different IP addresses. We have our internal and our external. So this one I'm never going to be able to get to. But if I try that one, haha, and we should be able to SSH straight into it. Voila, we're running inside of a virtual machine. And already had my keys. My keys were inserted into SSH authorized keys right there. This does give me the opportunity, though, to demonstrate terminating instances, right? But before we do that, let's take a quick look as the administrator. One thing that you're always going to be concerned about is the usage of your cloud, right? If you're managing this cloud, we can see we're over half utilized. And again, just throw zeros behind these numbers. You've got 80 of 120 CPUs or 800 of 1200 used. And what you might want to do at this point is actually scale out your cloud, because you're gonna run up against resource limits here pretty soon. So let's kick that off in the background. That'll take us 5 minutes to do. So I'm going to move back over to the deployment screen, and I'm going to click on Nova Compute. That's what's providing those compute resources, right? So I click on Nova Compute, and I'm going to add 3 units. I think I have 3 spare nodes here. 1, 2, 3. I do. Okay, good. So let's add 3 units of Nova Compute. That's going to double the size of my cloud effectively. And I'm going to confirm that we're going to add 3 Nova Compute units. We do that, and then this little graph is going to show me that I've got 6 units that are currently pending, or 3 units running, 3 units pending, and that's going to take a couple of minutes. If I look at my hardware here, I see I have a couple of nodes that are currently node 9, node 8, and node 4 are powered off, but they should be powering on here any minute. Oh, okay, cool, they're coming on. This might actually be an interesting time to take a quick look at what happens when one of these instances starts up. So I'm going to launch a tool that lets me watch these machines as they boot up and they get imaged. So this is node 9, which would be your node on the farthest right. The first thing we do is we boot into an ephemeral image, meaning we boot over Pixie. We pull down just enough of a disk running over iSCSI. It's an iSCSI target that launches us into the installer. The way we install these nodes, and the reason it goes so quickly, you can see the bottom lights are the hard disk lights. You see those 3 lights that are completely pegged? That's because we're doing a massive download, and we're going to untar this tarball and just do a write to those SSDs. It'll happen real quickly. It's 250 megs or so of data that just gets written straight to the hard disk. What we really like about that is, number one, it's fast, super fast, way faster than like a deb install or an RPM or a yum install, where you have to go through hundreds of packages and crack open each package and install that package and then run the post-it scripts. What we've actually done is completely repurposed the same exact image that we installed into Glance, the same exact Ubuntu image that we upload into Amazon every day. It's the byte for byte, the exact same image that gets written to bare metal. And so we're treating the metal itself just like a cloud. And that gives us the opportunity to do this very quickly. We've actually ported that same process over, and we can use the same process for CentOS, Windows, RHEL, SUSE, SLES. We can do the exact same thing. Basically, you take the same image that you would upload to a Glance, or the same AMI that you would download and run in an Amazon, and MAS, the metal as a service, the thing that's starting these machines and installing the OS, it can take those tarballs, format the disk, lay down that base image, and then do basically a bootloader install, and then reboot the system. So we're already running in the first boot you saw was the install process. This is the real process. Node 9 is now up and running. And if we watch, it's not going to be interesting at this point. It's just a running, working Nova Compute node with a login. So I'm going to kill that off at this point. Where the interesting work is happening is going to be in the squid logs here, and it's fetching the data that now makes that completely generic server that didn't have any personality. It's what's going to turn that server into a Nova Compute node. So it's pulling down a bunch of stuff, and we're getting lots of hits to a squid cache. It makes every squid administrator very happy. And then the bottom screen, you can see what Juju is doing to install those packages and then tie that back to the rest of the components of OpenStack itself. And so in just a few seconds, we should see this Nova Compute go from 3 running units and 3 pending to 4, 5, and 6 running units. More importantly, we should see the number of hypervisors available to us here go from 3 to 6, and we should see those pie charts show us that we now have even more capacity available to us in our cloud, right? And that's typically the most common workload and the thing that you want to do when you want to scale your cloud, right? That was the point of our talk here today, is how do you scale OpenStack. So we'll let this complete. Oh, look, there we go. So we've now got 5 running units. We're waiting on 1. I'm never patient enough. It takes OpenStack a little bit longer, always longer than I think it's going to take, to recognize the fact that it has more resources available. So we'll just give that another minute or so. I did say we'd kill off some instances, but I want to leave those instances running for a few more minutes, just to keep things consistent. I haven't really paused for questions, so thank you, sir, for being the person who reminded me of that.
The difference between static IPs and DHCP. Can you actually give them static IPs?
Can you give the OpenStack instances static IPs? Not really, no. Under what circumstance would you want to do that in a cloud environment?
I guess it will be easier to manage that you already know what IPs each node has.
Right, fair enough. So to answer your question, no, we don't typically do static IPs in OpenStack. Yeah, so I mean, there's a couple of ways of figuring out what your IPs are. In this view right here, you can see these are the IPs. You saw I couldn't get to this one because it's not actually connected to that system. You need to have actually that internal and the external. You can always see what the IP address is associated with a node. Yes, you can change it here from the administrator. And actually, you can associate I thought you could associate more than one floating IP. Maybe not. So no, changing is not easy to do here. You can choose it up front if you're the administrator and you know what IP is available. I think the more interesting solution to the problem you're getting at is proper name resolution of those instances, right? They're going to have a host name, they're going to have an IP address, but who's going to resolve that for you? And that's something that we're working on upstream in the OpenStack project to provide good name resolution in OpenStack. There's a few ways to do it right now, but none of it's really well baked into OpenStack just yet. Yeah. Yeah, that's how you get to, right? So just 1 second here. So I clicked on the hypervisors tab, and we now see we have 6 hypervisors. Or six nodes that are serving as hypervisors. We went from 3 to 6. We scaled that up, and you can see our pie charts have we're no longer 3/4 of a way through this cloud. We've got plenty of capacity available to us. So in our instances, I'm going to kill off these 3 instances that aren't going to do anything for us. So I'm going to terminate instances like that. Of course, you can do this from the command line as well. Now we've deleted those, and if we go back to our hypervisors tab, we've only got our 1 lonely instance running now, right? Yes, sir. Question. I probably can't answer it, but I'll try. Actually, it has 2. So we're SSH'd into it on one of these windows, right? So if I do an if config, I don't know what I was thinking. You're absolutely right. It is only a single. It is only a single NIC.
There's another instance somewhere that's running the Neutron part of things.
Yes.
Adding to that external.
That's absolutely right. Yeah. I'm sorry, I was confused at the beginning of the question. So if you want to look at Neutron itself, that's where the real geekery happens inside of OpenStack. So this is our Neutron gateway. I can inspect it here and see what machine Neutron is running on. And it happens to be running on node 0 VM2.mas. Let's log into that machine and see what's going on there. I can SSH to node 0 vm2.maz and get right into it. I can also juju SSH into Neutron gateway /0, and Juju will do that resolution for me. And I think that's what Jill was mentioning here.
You don't need to worry about what IP addresses you have to worry about what service you want to have.
So this is so now I'm on the Neutron gateway. And if I do an if config here, you'll see a lot going on. First of all, and most importantly, you'll see that this machine has two NICs, ETH0 and ETH1. Now, this is a fun little hack that we do on the orange box to make OpenStack work. Neutron requires two interfaces, an in interface and an out interface, just like any gateway would require. Unfortunately, the little hardware that we have inside of this box, the little Intel NUCs, only have a single CPU. And so we spent most of a week in London at a sprint beating our head against the wall. So how are we actually going to really deploy a useful OpenStack on the orange box? And someone had the epiphany that, hey, interfaces are cheap in virtual machines. Why don't we just run a KVM virtual machine on node 0 and make it our Neutron gateway? And guess what? It works brilliantly. So this is a virtual machine running on node 0 that we're using for Neutron. All the traffic to and from any of the instances flows through this machine, and now we've got two VMs. Now each of those ETH1, ETH0, we're then bridging here. So we've got a bridge that is connected to the 10.14 network, which is what I'm actually literally plugged into on my laptop here. And then we've got the external, the internal tons, and then we've got taps for taps that will be allocated as necessary. That is unfortunately about as deep as I can go personally on the implementation of Neutron. I would invite anyone else in the audience who's a Neutron expert to add to that if they've got more knowledge than me. It's one big. Actually, there's two VLANs, but there's one that we use for management of the switch itself and admin VLAN. It is a VLAN capable switch, but for all practical purposes of your real question, yes, it's one flat VLAN. I can possibly even access it. I'd need to get another IP address on that interface, but yes. Dumb, simple switch. You will almost certainly have something smarter than that in your production network. Yes, sir. The IP addresses of the physical hardware itself. So that's managed by the hardware manager, this thing we call Maz, which is what enables us to do this install really quickly, the thing that installed those instances. Maz itself it's not terribly innovative, to be frank, but it's really solid and really good at what it does. It's DHCP and DNS and PXE and TFTP and Squid, and this lovely web interface for viewing the machines. It's what takes care of installing OSs on the machines. It's what takes care of allocating IP addresses to those. It also takes care of name resolution of all of those .maz names to the IPs that they get associated. It tracks the state of each machine and serves up the appropriate boot image over PXE, which says either, hey, boot this image and install it yourself, or boot this image and boot from your local disk, actually. But that's all handled at the Maz level, and that's the 10.14.1. It's running a DNS server as well. It can only resolve the names that it knows about and the stuff that it can forward on to. What I don't have is, in this demo today, so this is our instance right here, our OpenStack instance, test2, if you remember. There is no resolution of test2. So if I tried to ping test2, it doesn't know how to get to that because we don't have DNS running inside of OpenStack in this example yet. Okay. Cool. So let's see. So let's deploy a real workload to this OpenStack, right? Let's go back to that Hadoop workload we were going to look at earlier. So here I have another example that another script that will help me out here. I'm going to run orangebox launch here. We'll take a look at what this is doing. Oh, I need to source my Nova RC and now run orangebox. Oh, I deleted a flavor. Now we get to debug. One quick second here. So this is a little bit annoying. The flavors that come stock have lovely integers. The flavors that, once you edit the flavors, they get UUIDs. So I had hard-coded a flavor number here. I'll change that to 2, and we should be okay. That's the only instance of it. So let's run that again. Voila. So now we've launched an instance from the command line as well. This is a lot more useful when what you're trying to do is something more programmatic. So let's take a look at the script, and this is kind of a good example of things you might do from a script when you're trying to launch instances in an OpenStack type environment. So of course you need to source that Nova RC that defines your endpoint and credentials. We create the floating IP up front, and so that's what gives us one of these accessible 10.14 addresses as opposed to the ones that are internal, only the 192s. We need to grab a couple of other UUIDs, the network UUID and the image UUID. And here we're going to do a Nova net list and find the private address. We're going to do a Nova image list and grab the trusty image. And then this is how you boot an instance, how you create an instance. This is like EC2 run instances against an Amazon. You saw the bug that we hit with, or the error that I hit with a flavor that didn't exist. But you tell it what key name you want, and that's what key gets inserted into your .ssh authorized keys. You tell it what image you want to boot, the network that it should be in, and then the security group that it should be part of, and then you can actually give it a host name at the end. And so the first instance we create is called jump server. What I do for this demo anyway, I create 2 instances. One is our jump server, and the other one is our orchestrator that will launch a bunch of other machines. The jump server can stay persistent for the length of a couple hours or a couple of days or whatever I need for the demo. But then the other instances get started and stopped from there. It takes about 20 to 30 seconds. I'm conservatively sleeping 40 seconds here, waiting for that machine to boot, and then associate the floating IP with that jump server so that I can then get to that jump server. Sleep for a couple of seconds, and then we go into that machine and we install some code. We give that machine its identity. We create this YAML file with some credentials, and then we're on to the next stage of deploying a workload. So here we're just waiting for that system to come up. If we go back and look at our instances, you'll see we still have our test 2, and we also have our jump server, and then we're just waiting for the first of our orchestrator machines to come up. And it is up, and now we're doing an update and upgrade. And I bet if we go over to our squid proxy, we're getting refreshes on those packages. And the system will be up here in a couple of seconds. And then we can start doing work with our OpenStack. Any questions at this point as we wait for the little mouse inside to turn the gear? Yes, sir. Lose a node, great question. High availability is your friend at that point, right? You want everything running in clusters. If the hardware node, it really depends on what service is running and whether that service is clustered. Okay? For our production deployments of OpenStack, high availability is required, absolutely required in any enterprise environment. The various services that make up OpenStack have varying degrees of cluster ability. So we can just kind of go down this list. Nova, in particular, if you lose a Nova, you lose the instances on that machine, which is going to be inconvenient for the users of those instances, of course. When you know you need to evacuate a node, you can't actually live migrate. Depending on how things are set up, it is actually possible to live migrate instances from one node to another. So if you have some warning, you're in a maintenance window and you need to replace some hardware, you can gracefully back things off, remove that node from Nova Cloud Controller, and then take it down. But if you just hard lose a Nova Compute, you lose the instances on it. Quantum, the Neutron, that's one of the key places that you really want to use multiple instances of Neutron. And high availability of Neutron it's reasonable. It's doable. There's some gotchas, but that's the place where if you lose that, you lose network access to your instances, and that's never good. Yes, sir.
So when you were saying there, when you lose the node, is it easy to recreate it on a different node?
If the instances are backed by a volume and you have a snapshot, sure, it's actually quite easy to launch an instance from a snapshot or from a backup, or if the backing disk is in Cinder. If it's, but it's going to be whenever that last sync was. There's snapshotting, no, it's not automated. Using a Cinder-backed disk would be something that you'd need to set up ahead of time, and then the data that's stored in Cinder, sure, is not on that Nova node at all anyway, right? Yes, sir.
If the underlying hypervisor is something like ESX with HA, is there support for that at all?
I have no familiarity with ESX, but if the hypervisor itself supports HA, I would hope that you've got more protection against something like that. I'm not familiar with ESX, though. Sorry. Okay. Okay, so let's try this right quick. First of all, let's rsync over our Hadoop example to that machine, and then SSH to that machine. And let's kick this off. Let me just check let's look at our hypervisors here. Sweet, we've got 24, we've got 18 available. We should have plenty of room to do this. So now we're going to deploy a workload to OpenStack, and hopefully we'll see before the session ends here, a Hadoop running on top of OpenStack. There was another question, I think, over here. I have to look somewhere. Yes, sir.
So which part takes care of actually powering on physical servers?
So that part is MAS, Metal as a Service. It's not part of the OpenStack project, but we work very closely with OpenStack to ensure that MAS can deploy OpenStack. MAS is an open source project from Canonical, built around Ubuntu. Stands for Metal as a Service. Anytime we deploy an OpenStack, we use MAS in that environment. Step one is grab a server and stream out a server, apt-get install MAS on that machine. Once that's up and running, you add the physical hardware into it as basically inventory, and we've got some automated methods for enrolling machines. But entering a machine is really a matter of, typically it's just booting the machine over Pixie, and it can auto-discover and take care of everything. If it's IPMI, it can even insert the credentials to turn the machine on and off. If it's not, you may need to manually configure a few things, mainly the power type. So Maz can power on lots of different systems. So you see Moonshot, you see ILO, you see IPMI. In most data centers, it's an IPMI, but sometimes it's this Cisco UCS or something. But whichever one of these it might be, you would then enter the credentials for how to boot that, how to turn that system on and off, and query it and reboot it and so forth. In this case, Intel AMT, Asset Management Technology, is the really small consumer-y power management system that we have on these notes. It's the best that we can get, and it's kind of wonky. So we end up with, fingers crossed, but we haven't had a problem yet with them today. But yeah, but IPMI is not much better. I don't know if you've been around IPMI, but it can make you pull your hair out sometimes too. Does that help? Okay. All right, so let's take a quick look here. So we should see more instances launching. Holy cow, we have blown through our allocation. So this might be a good time to scale your cloud again, right? Yeah, so we've got instances starting up and running. Let's come back over here, and now we'll point browser to this machine. Let's see if our Hadoop is coming up. Okay, so we've started to deploy some things. We've got our MySQL. The others are coming up. As you can imagine, red is never good. So that one might take a little bit of debugging to look at. But this is, if I had to guess, I would think our problem is that we needed more instances than we had capacity for. I probably hit that limit, and that service didn't make it onto another node here. Okay, so we've got 8 minutes left. Want to try blowing this all away and recreating it all over again in 8 minutes? Can it be done? You look nervous. No? No, not interesting. Okay.
Oh, no, not this.
No? Yeah, I think it will take more than 8 minutes. I actually don't think I can finish it quite in that much time, but we can try. We can try. So let's actually, the reset's going to take 2 minutes, so it's only going to leave us 6 to do the rest. We'll see. Yes, sir.
So you install like Elasticsearch through the GUI.
Yes, through that GUI. Yeah, absolutely. You can just as easily as running that .1 deploy script. I can just as easily have drag and dropped a YAML file onto that GUI and said, deploy this onto OpenStack. And it's actually, you can search from it in the, you can search for it and just add it right on there. It's actually quite easy to do from the GUI. Are you familiar with Elasticsearch? Yeah, cool. Yeah, so in that demo, we load the entire works of Shakespeare into Hadoop. We run it's not a big data, but it's a big data job to index all of that. And then in Elasticsearch, you can type any word in and just search the entire works of Shakespeare. It's kind of cool. Yes, sir.
Is it possible to deploy VMs without windows? Meaning, for example, use Pixie to install the VM?
Really good question. In OpenStack, can you boot an instance with no image, but have a Pixie server inside of OpenStack to supply that? I've never done that before. I can see some issues with running a rogue Pixie server inside of an OpenStack, right? So I'd have to think through that one a little bit more. That's an interesting idea, though. I've never really considered that.
I've actually done like
In a VM, interesting. Okay. And how do you manage that Pixie server in a semi-public IP space like that?
So I quickly boot up my PC that is like over
Interesting. Okay, that's cool. So that's a feature of iPixie, that's specific to iPixie as opposed to gPixie. Cool. Interesting. Okay, so now all of our machines are powered off. Good, we've done that, and now let's see how quickly we can stand this up. We'll do Juno again, just since the squid cache should be hot now. We can kind of watch what goes on if you're interested in that. Yes, sir.
Can you talk a little bit about the authorization model can create consistent
Yeah, good question. So instances is definitely in the realm of non-privileged users. So I should have done that. If we get this up in time, I'll create some non-admin users. I meant to do that and it slipped my mind. Instances is sort of the one thing that non-root or non-admin users would do. And they can create instances within their quota, within their whatever amount of quotas they have available to them. They can also upload their own images. So they can create their own image and put that into the store, and then they can boot that image. Images by default aren't shared across users unless the admin user adds that image, right? Users can create storage, again, all within quota. So you quota how much those users could do. Users you mentioned authentication. Through the GUI, they're authenticated name, password type credentials. On the command line, it's usually an admin secret, an auth token, basically, that they can pull from the GUI and then put into that Nova RC file, just that environment variable that they would source. And then with that, the user can run Nova commands or glance commands or whatever to interface with it over a command line. Mm-hmm. Yeah, it's pretty slick from an automation perspective. I see we have a minute or two left for the next speaker. Yes, sir. Yep. So in that flavor, when we created those flavors or modified those flavors, you can define how much local storage an instance gets, and by default, most instances will have some amount of local storage, 10 gigs or 20 gigs of local storage. Local meaning it's actually, that part of the disk is actually on the physical node that is the Nova compute node, right? So it's faster, especially these SSDs. It's not writing over a network or reading over a network. What you lose, though, is the high availability that this gentleman was asking about, like what happens if I lose my Nova compute, your data just kind of goes away if it's on local storage. Again, that maps very much to the AWS EC2 way of doing things. There's ephemeral disks that are local. There's EBS that can be highly available or remote storage. In our example here, we're backing that with Ceph. So Cinder is the interface on top of Ceph, storage underneath. Again, storage is very pluggable in the OpenStack world.
By the way, the next speaker is coming in for another half hour. Take a break.
Oh, really? All right. So I don't get to just bolt out of here. Then we're actually going to wait for this to complete. Looks like it's almost done. I think we'll get there in another minute or two, and then we can just blow through that script instead of copying and pasting every line. Yes, sir.
How big is your squid cache so optimize your demo class?
I think it's allocated to 40 gigs. So sudo etc maz. Let's see, maz. Grep squid, grep proxy. There it is. Maz proxy.conf. Looks like we have 512 megs of memory, maximum 40 gigs. Our spool Maz is set to 40 gigs here. That's big enough for that's big enough for all packages that I would need to install on one of these systems. There's only 120 gig disk on the root disk actually, but I have the 2 terabyte, so I've got plenty of space. We can take a look and see how much of that I'm using in practice. So let's sudo du-sh. Who wants an over and under on this one? I'll give you 20 gigs. Over or under? Under? Over? 3 gigs. It's really not a whole lot. I mean, we're installing the same stuff on every one of these machines. You know, we start with a 250 250 meg Ubuntu image, and then we apt-get install a handful of debs. I guess we can't really var spool maz proxy find dot dash type f. So about 5,000 files, and then 3 gigs over 5,000. So 600K per file is about the average .deb size. You know, some are bigger, some are smaller, but seems pretty reasonable. Yes. CentOS, yep.
Yeah, how do I get the view of what you have?
Yeah, good question. So Maz itself can deploy CentOS to physical machines. So it's as simple as uploading an image into Maz. So Maz has this images tab right here, and you'll see that we've got Ubuntu images, but we've also got CentOS images loaded in here as well. And so I can go into any node. So like take node 9 for instance. I can edit this node, and I can say that what OS I want is CentOS. I want CentOS to go onto that node, and I'm going to save that node. And then instead of using a script, I'm going to start this machine from the GUI here. So I'm going to say start machine node 9, and then we can watch that machine, node 9, get CentOS installed on it. I'm just gonna, hold on a second. Let me let it power on first. There's an interesting bug that if you have this is a really weird corner case, but if you have the remote console attached to the node before it turns on, you're limited to 10 megabits for the life of that boot. But if you attach to it after it's booted and E1000, the kernel module loads, then we get gigabit. So hopefully I didn't disturb that, or else we'll be here for a while waiting for that machine to come on. So the first part of the answer to your question is, so Maz supports the CentOS, writing those CentOS images to the machine, and we should have a CentOS. We should be able to SSH in this machine running CentOS 6.5 in a couple of minutes here. The second part is about the way we install the OpenStack itself using Juju, and we're working on CentOS support for Juju right now. It's not there yet, but we'll get to it middle of next year roughly. And that's part of the way that we deploy OpenStack.
So you need both Juju and Maz on Ubuntu in order to deploy.
Today, to do what we did today, yes, this method of installing OpenStack. as I said earlier, there's lots of ways of installing OpenStack. Puppets. There's certainly Puppet manifest for OpenStack. There's Ceph deployed OpenStack. There's Ironic deployed OpenStack as well. It looks like possibly next year Ironic may become an official way of deploying OpenStack by the OpenStack community, and that's wonderful. It's great to have multiple ways of installing it. Hopefully I try to focus more on OpenStack than the tooling, but inevitably the tooling will come up.
I like that it's UI-based. I'm just hoping there will be equivalent something on the other side of the world.
Yeah, sure. I like I said, I expect the Juju support for CentOS to land next year. We support Windows now. Juju can deploy workloads onto Windows, so CentOS should be easier than deploying workloads to Windows, I hope. Let's see if Node 9 is up yet. It is. So we've probably done the first boot, and now we're booting the CentOS image now. And let's check our second deployment. All right. We've got lines. Lines are good things. And we're finishing adding those relations. So we're almost there. So now we might be able to log into Horizon. All right, so there our OpenStack has deployed. You can see here. I think it's a little faster than last time, right? Last time it was more like 1,000 seconds, right? So just over 10 minutes. We will go into here, and we'll just run our configure OpenStack script. Yes. Oh, by the way, thank you so much for asking that question. They're on Launchpad. They're open source. BZR branch, LP colon, orange box examples. I can push it to GitHub, to mirror it to GitHub, if that helps. Yeah, every single thing you've seen today is 100% free and open source software. There's not a line of proprietary code in anything I've shown you here today from the, well, I guess technically I was using Chrome as a browser, but aside from that, yeah, no. We love our open source free software. All right, OpenStack is configured. We've got images. We've got instances that we can now launch. So let's launch an instance, and then I think we'll call it a day.
Did that revert all your changes to flavors?
Yes. Actually, well. Yes, those are the manual tweaks that I made. This was just the stock one. So test 3, one instance, boot from image trusty. I'm going to choose private network this time. nic1. And then we want to associate a floating IP. We've got our floating IP, and not up yet. There we go. Voila, we're in. From scratch. Thank you very much. Yeah, was there another question? Yes, sir.
For the roles that each of the nodes gets, is that defined whether as the YAML file or is that an allocation role that's fixed on the ground?
Boy, that's a great question. Let me show you. And by the way, you're welcome to stay, and if you want to go, it's no. We're into the break now. Thank you for reminding me we're in a break. Outstanding question. So in the YAML file itself, which I'll demonstrate one thing right here. So I've been using YAML files that are locally located on this machine. Locally located. It's a fun term right here. But I could just as easily in this GUI click export, and that would export a YAML file that I can now drag and drop onto any Juju any Juju system anywhere I want. And in here, there's a bunch of different ways you can specify how and where things get installed. So Neutron, for instance, that's the one that I said I can only run that on a virtual machine because only my VMs in here have more than one NIC. So on Neutron, you can see charm, num units, options, constraints. So constraints here, I've defined what I require for placement of this service. And the machine that it gets has to have a tag in MAS of virtual. So in MAS over here, you can see my virtual machines have a tag that says virtual, and these are the nodes that are virtual. And then I've also got a physical tag that shows me the machines that are physical. And if we look in here, we can see there are some services that require physical machines, or that prefer physical machines. So Nova Compute, for instance. Actually, this is interesting too. So on every one of our Nova Compute nodes, we're also running Ceph. So in our reference model, in the Ubuntu OpenStack reference model, we like to run Nova everywhere, and we like to run Ceph everywhere, and just give portions of every machine, especially on big honking machines, portions of every machine can host some VMs. Portions of every machine carves up its extra disk as a Ceph disk, and then the other services, the MySQLs and the Rabbits, are sort of evenly distributed amongst the rest of the systems that are necessary, and we typically run those inside of LXC containers. Also for constraints, tags is one constraint. You could also require a certain amount of memory, a certain number of CPUs, a certain amount of disk as well. And that's just sort of the placement aspect of it. And then in the GUI, I didn't show the machine view, but if you're really curious about what services are running where, when I've shown the GUI, you've seen this sort of service view, but there's also this machine view where you can see, as I said, you've got Nova Compute and Ceph running here. You've got Nova Compute and Ceph running here, Nova Compute and Ceph running here, so they're co-located. And then on this machine, you've got Salometer, you've got Dashboard, MongoDB, and Heat are all running on this node. And then if you want to create a new, you want to add a unit, let's add a unit of, not Dashboard, that one's not interesting, but let's say we want to add a unit of MySQL. We want to create a MySQL cluster. And I click Add Unit. And instead of just allocating a whole new machine, I say let's manually place that new MySQL unit. Whoops, did that not go? I want to confirm that. Oh, sorry. New unit, MySQL. I want one new MySQL unit. Add unit. So now I have a MySQL, and I want to put it on this machine. Doesn't look very busy. I want to put it on this machine. And so now it's placed, and I click commit, and for some reason that didn't take, but you get the idea. I can tell it where I want to put that. You can also carve machines up into containers. So I can say I want to add an LXC container. Having a create, here we go. So I've created an LXC container, and I've put 1 unit of MySQL in that container. And I tell it confirm, and then if we go back to the services view, you see MySQL right here. Zoom in a bit on it. You're going to see this one's going to go extremely fast because it didn't have to start a whole physical machine, install an operating system, and then apt-get update, apt-get upgrade, apt-get install MySQL. It's simply going to create a container on that physical system and install MySQL in that. Cool? All right. Well, thank you very much. I'm going to shut down, and I'll be around if you have any other questions.